Uh, the talk will be presented by William Bowman.
Thank you. So can everyone hear me all right? A bit loud. Okay, great. So before I get started, I want to give a quick shout out to my co-authors who are all here at POPL'. So this is joint work with Nick Rioux, who's an undergrad at Northeastern with myself and Amal, and my colleague Youyou Cong, who is a PhD student at Ochanomizu University in Tokyo. Okay, so today I'm going to tell you about type-preserving CPS translation of the calculus of constructions with sigma types, and why it is not possible. So this is part of a larger project whose goal is to develop a verified type-preserving compiler for Cong, and for dependently typed languages like Cong. Okay, so let's start with dependent types. What are they good for? Well, I'm here at POPL', so we all know everything, right? So we now have verified compilers, verified operating systems, language semantics, crypto primitives, and protocols, all verified in Cong, right? It turns out it's very useful to be able to simultaneously develop a program, fully specify its behavior, prove that the program meets its spec, and then have a machine check your work, right? And this is great. So we have lots of code verified in Cong, but that is not the end of the story, right? When I write a program in Cong, I'm typically going to extract it to Ochanomizu, and now it's not clear that my verification still holds. And then Ochanomizu is going to compile it further down to assembly. So our verification story looks a bit more like this, where I have strong guarantees in Cong, but then each stage of compilation can undo my verification, right? I hear your complaint. We need a correct compiler, right? We want to prove correctness. So what we're going to do is have a correct compilation story. We're going to verify our Cong program and also verify each stage of compilation. That way we know that the program we end up running is guaranteed to be the same program we verified. But this is not the whole story. It is kind of the whole program story. We need type preservation, though, because we don't write whole programs. When we write a program component, and that component will inevitably be linked with some external components, right? So when I write some Cong component and it is verified at some type, I then extract it to Ochanomizu, and now not only am I not sure about my verification conditions on that component, I'm going to link it with some unverified code, right? So now I have two places where I could be introducing bugs. My compiler can undo my verification, but so too can linking. And then I'm going to compile this down further, down to assembly code. And I've compiled both my verified component and my unverified component down to assembly. And then I might link with even more unverified code, like the language runtime or the operating system or some low-level C libraries. And now all of these points, our compilers and our linking, can undo this verification effort. And what happens now is I can write a small verified program in Cong, extract it to Ochanomizu, link with some unverified code, and cause my verified Cong program to jump to an arbitrary location in memory. And if I'm very lucky, I get a seg fault. And the state of the art in avoiding this is to tell the programmer to be careful. So we've gone through all of this verification effort, encoded our program invariants and our rich dependent types, just to tell ourselves, oh, I can keep all those in my head when I'm linking. No, I say, do not be careful, be well typed. Our goal should not only be verified, but type-preserving compilers all the way down to some sort of dependently typed assembly language. So we want to preserve all of our typing structure, and then we have verified compilers, and when we link, we can have type checkers automatically enforce our invariants. So that's the grand vision. Now, I know you're all on board. Great, let's preserve some dependent types. So how do we do that? The first step is to open up F to tau. So F to tau is the seminal paper on what a type-preserving compiler needs to be, right? So it's going to be a sequence of type-preserving transformations, and the very first one is CPS. Fine, our goal is to do Cong, so we'll go and extend this to the calculus of constructions. The continuation passing style transformation. So this will make control flow explicit in our language. So the problem is that about 15 years ago, Barthe and Uustalu tried to do just this. And what they find is that once we have sigma types, type-preserving CPS translation is not possible. Well, that's a bit odd because I thought I had a POPL paper that said I'm doing type-preserving CPS. So what gives? Well, of course, what they prove is that no CPS translation is possible along the same lines as f to tau. We will therefore proceed along less impossible lines. Okay, so let's take a quick look at why the not translation, the standard type CPS translation by double negation, is not possible. Now, intuitively, the CPS translation is going to take every expression of type A and turn it into a computation of type A arrow bottom, so not A, right? Now, the problem with this in a dependently typed setting is that dependent types have to decide equivalence between expressions when they're type checking. Now, when we have expressions E and E prime of type A and we want to decide whether they're equivalent, well, one way we can do that is just run them down to values of type A and compare the values. But when we do CPS, these expressions are going to be transformed into computations, C and C prime, of type not A. And now it's not clear how we can run these computations. So our interface here, not A, says you have to provide a continuation, and only then will I run this computation. And at the end of the day, what you will get back is of type false. So how do two things of type false being related tell me anything about my computations? And what continuation should I even provide? So this is the essential difficulty in doing type-preserving CPS for dependent types. It's that after we do CPS, deciding equivalence of computations becomes hard. Okay, now this is a very formal paper. So we are now going to leave the realm of intuition and see some math. So let's start with the formal definition of type preservation. So our goal is a type-preserving CPS. So this is type preservation. In our source language, we have a term E of type A. And what we want to be the case is that we compile E down to E plus, and we compile A down to A plus. And it should be the case that if E had type A in the source language, then E plus has type A plus in the target language. Now, the problem is that when we do the call by name CPS translation in the presence of strong dependent pairs, type preservation, so sigma types, type preservation is going to fail. So we'll start here with the typing rule for second projection of a strong dependent pair. So we have a pair E with the first component A and the second component of type B, right? And here B, the type B, can actually depend on the first component of the pair. So in the type, that's bound as X. And then when we do the second projection, we replace X by the first projection of E. So what we have here is dependency. We are copying a program, part of the program E, into the type. Now, if we take a look at this expression second of E as a machine might look at it, intuitively what's going to happen is we're going to take E and run it down to a value. And only after we have a value will we do the second projection. Now, the problem is that type preservation mandates that we show this term, second of Y, has the type B plus with the translation of first of E replacing X. So this is what we need to show. But by this typing rule second, all we actually have is that second of Y has type B plus with first of Y for X. We copy Y into the type, not E. So how can we show this? Well, it suffices to show that first of Y is equal to the translation of first of E. That's a sort of interesting condition. And in this intuitive presentation where I've just set Y equal to E plus, looks fine. But remember, we're actually doing CPS here. So we have lambdas sitting in all of our terms. So what we actually have is E plus applied to a continuation. Lambda Y, some type, and I take the second projection of that Y. Now I'm going to, for your sanity, ignore some of the details of CPS and not write all of the continuations. But this term, E plus applied to this continuation, essentially has the same problem. Now, the problem is that in order to type check a lambda, we assume that we have some variable Y that is arbitrary beyond its type, and we check the body of our lambda. But how can we show that first of Y is equal to the translation of first of E when Y is arbitrary? Okay, so this is our goal. We have our computation applied to its continuation. We have an arbitrary Y. We need to show that second of Y has the type B plus with first of E for X. And it suffices to show that these two terms are equivalent, first of Y and the translation of first of E. Now, to see why this might be true intuitively, know that in CPS, what's going to happen is that this computation E plus is going to run down to a value. And once it gets a value, it will pass that value to its continuation as the variable Y. So intuitively, this should be true. We also know that based on what CPS is doing, that the computation that represents the translation of first of E is essentially going to perform the first projection of whatever value E is. Right? So intuitively, that should be true. If we combine these two facts, then we get that first of Y is equal to first of translation of first of E in this particular context. Okay, so we have two problems to solve. First, what is the value of a CPS computation? And second, how do we actually remember that value when we're jumping to a continuation? Okay, so to answer these questions, the key is to stop using double negation. Instead, we're going to use a different CPS translation, and it turns out that CPS translation can be made type preserving. So in particular, we're going to use CPS with an answer type polymorphism. So whereas with the double negation translation, we assign computations types like not A, with the polymorphic CPS, we're going to assign computation types like for all alpha, A, arrow alpha, arrow alpha. And now this changes our interface to our computations, whereas before we just provide a continuation, now we have to provide an answer type B and a continuation. But as a result, instead of getting back a false, we get back a value of type B. Okay, so how can we use this to figure out the value of a CPS computation? Now before I said that the key is looking at equivalence between terms. Before we weren't sure how to compute equivalence of two computations, but with the polymorphic answer type, we can get that the computations C and C prime at type for all alpha, A, arrow alpha, arrow alpha, these are equivalent if we apply C and C prime to the underlying type A and the identity function, which will act as the halt continuation. So we essentially locally run these computations to extract their value. And as a result, instead of getting back a meaningless value we don't know what to do with, we extract the meaningful underlying value of type A. Okay, so that's the intuition. Formally, what we do is we add this definitional equivalence to our typed target language. So this equivalence is based on the well-known continuation shuffling lemma, also known as the parametricity condition or naturality in the literature. And what it says is that when we have a computation E1 applied to an answer type B and this continuation, what we can do is essentially shuffle this term around so that we use the continuation as a function applied to the value of E1, where the value of E1 is E1 applied to the identity function, right? So this rule lets us stop reasoning in CPS and instead reason about functions applied to values. And importantly, it tells our type system how to do that reasoning as well. Okay, so essentially that value of that we were referring to earlier is just E1 applied to its underlying type A and the identity function. Now, of course, we can't just go about adding random rules to our dependent type theory, so we have to prove that this is sound. And the way we do that is we use the well-known parametricity translation to give a model of our target language in the extensional calculus of constructions. And in that model, we can prove equiv-cont as a free theorem as a consequence of parametricity in that model. And the details of all that are in the paper. Okay, so if we return to our example, we're trying to show that second of y is well typed in a particular context. We now know how to write down the value of E+. And with just this rule, we can actually complete the second part of our proof. We can show that the first projection of E+ is equivalent to the translation of first of E. And the way we do that is we say, okay, well, first, the translation of first of E is essentially going to be E+ applied to the continuation, lambda y, first of y. Now, by equiv-cont, we can shuffle that around, and we get that the continuation, first of y, lambda y, first of y, is applied to the value of E+. And in one step of beta reduction, that reduces to our goal first of the value of E+. Okay. So now we know what the value of a CPS computation is. And we need to figure out how to remember that value when jumping to a continuation. Okay, so back at our example, what was happening is intuitively y in the body is equal to the value of E+. But formally, y is arbitrary. So how do we bridge this gap? Well, what if we just make this equivalence that we need part of this typing rule? Okay, so this term here, E+ applied to its continuation, is essentially the computation E+ will at some point jump to this continuation, lambda y second of y. So let's introduce a jump to form. It says we have computation, when it finishes running, it will jump to this continuation. And This jump to form will have a new typing rule that will just remember the equivalence we want, lambda y, e plus applied to id. Okay, so formally we add the following typing rule to our target language, where we acknowledge that jumping to a continuation is not really the same as application. Instead, when we have an e applied to an answer type and a continuation, we're going to make sure that our computation has the right polymorphic type, pi alpha, a arrow alpha, arrow alpha. And then we're going to just type check not the lambda that is the continuation, but the body of that continuation under the assumption that x equals e applied to id, so the value of that computation e. And again, we can't just go about adding type rules, so we prove that this is sound. But what's really interesting about this proof is that it essentially corresponds to the A and F translation. It translates all uses of this tcont typing rule into a use of dependent let. And in CIC, dependent let carries an additional equality that will nicely encode our tcont equality. Details of that are in the paper as well. Okay, so now we know how to remember the value of a computation when jumping to its continuation. And we can complete our type preservation proof. So now our goal is we have e plus is going to jump to this continuation, lambda y second of y. So we go above the line and we remember that y is equal to e plus applied to id by tcont. By the proof we saw earlier, we know that first of e plus applied to id is the same as the translation of first of e. By transitivity, we get our goal. First of y is equal to the translation of first of e. Okay, so far I've been looking at the call by name translation and sigma types, because this is what Barthe and Uustalu prove are not type preserving. But in the paper, we actually take a look at the call by value translation as well. And call by value is in some ways more broken than call by name and sigma types. It turns out that since call by value forces every expression down to a value, any dependency is essentially broken by the call by value translation. So, for instance, if we just take a look at pi types, we have E1 applied to E2, and we have the same pattern of dependency. So the return type B, we copy the argument E2 into that type. And if we look at our informal machine semantics, we're going to force E1 to a value, force E2 to a value, and we have Y1 applied to Y2, and we need to show that that has the type B plus with E2 for X. But of course, that's not what we have, because what we have is Y1 applied to Y2, substitutes Y2 into the type. But we can use our same two typing rules to show that the call by value translation is type preserving as well. And note that the call by name, it's not surprising that the call by name translation worked, because if we just look at how the machine would implement it, it would not force E2 to a value. Instead, it would be syntactically in application position and copied into the type. So the lesson here is that call by value is actually a more interesting translation for looking at these dependencies, and we should sort of expect that any dependency will break in the call by value translation. Okay, so at the beginning of the talk, I was talking about compiler correctness. We don't just want type preservation, that's great for linking, but we want compiler correctness too. So we go ahead and prove correctness of separate compilation. If we have a term E linking with some substitution gamma in our source language and it runs to a value, then we can separately compile E to E plus and gamma to gamma plus, link them in the target language, run them to a value, and we will get some value V prime that is equivalent to the translation of V. And what's interesting is that type preservation in a dependently typed setting essentially forces us to prove separate compilation. Because our type system has equivalence built in, we have to show that equivalence is preserved by our translation. So if E and E prime are equivalent, then the translations are equivalent in the target language. And since our definition of equivalence is defined in terms of reductions, we have to show that reductions are preserved. So if E steps to E prime, we translate E into E plus, translate E prime into E, that's a typo on my slide, E prime into E prime plus. Then it should be the case that E plus still reduces to something equivalent to E prime plus in the target language. And we combine these two lemmas, essentially gives us correctness of separate compilation. Okay, so at the beginning I also talked about scaling to calc, right? I want to handle calc, not just calculus constructions. So far we have the CPS translation from CC to our typed intermediate language CCK. And our goal is to get from calc to calc-k down to all the way to some sort of dependently typed assembly. And in between is quite a lot of work. And we're actually aware of one hurdle that stands in the way, because Barthe and Uustalu proved there was another hurdle. They proved that no type preserving CPS translation can exist, I quote, once we add dependent case analysis. So once we have inductive types, we have dependent case analysis. Thankfully, they require that your CPS translation admits call CC, and in particular admits call CC in certain contexts. Answer type polymorphism does not admit call CC. We therefore give a sketch of how we can extend our translation to dependent case analysis and give a proof sketch of that in the paper. Okay, so in conclusion, type-preserving CPS translation of sigma and pi types is possible if you stop using double negation. The key is to remember the value of a CPS computation when jumping to that continuation. Thank you.
So your jump reminds me a lot of other examples of calculi that make a strong separation between user lambda and user application and continuation jumping and continuation lambdas. Do you make the lambda distinction, or is there still only one lambda?
Right, that's a good question. So in this calculus, there is still only one lambda explicitly. But as you can see in that typing rule, implicitly any lambda that's used in that continuation position is different. It's never type checked as a lambda. And as future work, we do want to look at, well, what happens, can we make this more elegant, simpler, or get some advantages by separating out those two lambdas and making continuations a separate concept?
Yeah.
That's a good question, thank you.
More questions?
So by going to extensional type theory, you lose the decidability of type checking, right? Why do you then justify this approach? Why not go full realizability and just use some crazy type language and prove properties on this, just like what Derek was advocating for this morning by just stating that it satisfies from some logical relation?
Right. Right, so that's a good question. So our proof technique, as you mentioned, does use the extensional calculus, and so we don't actually have a proof of decidability of our typed intermediate target language, which is not great if we want to enforce type checking at link time. We do, however, conjecture that our language should be decidable, and we could change our translation so that we could remove the extensional calculus from this altogether, and we give an explanation of how we could do that in the paper, but we haven't done that yet, that's true.
Yeah. I was wondering, can you handle like a hierarchy of universes? Because I guess you have to choose a universe level for your return type in your CPS translated.
Yeah, so that's a good question. So this polymorphic answer type translation relies on impredicativity of whatever universe the answer type lives in. And so we talk about this at some length in the paper. It's not quite clear how to extend to the universe hierarchy of Cong. But we have sort of two approaches. The first is that we only need this impredicativity and this particular encoding at the base universe, the base computational universe, right? Because we're doing CPS in order to implement programs. We don't need to CPS all the type level functions, right? So we should be able to avoid CPSing most of the hierarchy. And so we're trying to investigate if we can make a sort of two-mode CPS translation where we use this for an impredicative computational universe and use maybe double negation or something else at all the higher universes. The second approach we are thinking of is, well, since we're passing in the answer type from the context, maybe we should use universe polymorphism so that the context also has to pass in the universe it wants to use. And I'm not very familiar with the meta theory around universe polymorphism, so I haven't looked at that in any detail, but it's a sort of intuitive thought we've had, and we plan to investigate. Thank you.
Okay, I should at least have one question here from Anonymous. Is anything lost by using answer type polymorphism instead of not? In other words, is there any gain to using not, or any gain by using not, I think? But
yes. So what we lose is the ability to implement control effects altogether. And with the double negation translation, you can implement control effects, but you can also implement false if you want. So There's a bunch of work on how can we actually safely implement control effects in a dependent type theory, and we've thought a little bit about how we might mix these two approaches, because it might be useful for optimizations and the sort of thing in a compiler to have control effects. So yes, something is lost, but for the moment we're worried about soundness, so we haven't thought about how to regain control effects yet.